Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. I welcome you to lecture number 9 of Data Communications and Computer Networks. This course is being offered at the Department of Computer Science, ComScience University Islamabad, Lahore campus. Today we'll talk about broadcast and multicast routing algorithms. Then we'll discuss reverse path forwarding. It's a controlled flooding mechanism to transfer data to different multicast nodes. Then we'll discuss distance vector multicast routing protocol, DVMRP. It's based on distance vector. Then we'll discuss protocol independent multicasting, PAM. We'll discuss its dense and sparse mode. The learning outcomes of today's lectures are: number 1, to understand the problem of multicast routing algorithm. So multicasting is in fact a subset of broadcasting. So we'll see how we can achieve multicasting and what is the problem statement of multicast routing algorithm. Then we'll try to compare distance vector multicast routing protocol and protocol independent multicasting. So before we start discussing today's lecture, let me quickly remind you what we have covered in the last class. So in the last class, we talked about Bellman-Ford algorithm, and we discussed the working of Bellman-Ford algorithm. We tried to understand it with the help of an example. Then we discussed RIP, that is making use of Bellman-Ford algorithm. Then we discussed different problems of Bellman-Ford algorithm, like the count to infinity problem. And then we try to identify its solution. Then we also try to establish the case of hierarchical routing, discussing that these routing protocols such as OSPF and RIP are not scalable, so we need to divide the network word into different autonomous systems. And within the autonomous systems, we can make use of either OSPF or RIP or interior gateway routing protocol. But whenever we have to transfer data in between the different networks, then we may need to make use of the de facto standard, the de facto routing protocol known as border gateway protocol. So then we did discuss border gateway protocol in detail. Today we'll talk about broadcast and multicast routing. So let's first talk about the problem of broadcasting, because multicasting is a subset of broadcasting. So when I want to broadcast a packet, this means there can be two different ways in which we can achieve it. Number 1, which is represented with the help of figure A. So it's called n-way unicast, right? That is, that if R1 has to send copies, or R1 has to broadcast a packet to all the other nodes in the network, so R1 will send n copies of the same packet. So this is called n-way unicast. Right. So this means that R1, in order to broadcast a packet, will send n number of copies of the same packet to all the nodes on the network, right? So, but it has several drawbacks. So the first drawback is its inefficiency. What if the source node is connected to the rest of the world via a single link? In this example, R1 has to send n number of copies using this single link. So this means the n separate copies of the same packet will traverse this single link. So it would clearly be more efficient to send only a single copy of a packet over this first hop to this R2, and then have the node at the other end of the first hop make and forward any additional copies needed, right? So rather than R1 sending n number of copies to R2, R1 should send only one copy to R2, and R2 can generate multiple copies of, depending upon the neighbors, can generate n number of copies of the same packet, each for a link. So this sort of duplication is known as source duplication, where the source is sending n number of copies to all the other nodes, depending upon the number of nodes in the network, right? There are additional drawbacks as well, by the way. For example, here less of the broadcast recipient, right? So in reality, we need to have some additional protocol mechanisms for multicast group membership to identify the destination machines, or we need to have some sort of destination registration protocol, right? So this obviously involves additional overhead. The other way to do is to have this in-network duplication, where the R1 will be sending one copy to R2, and R2 will make the copies for each of its outgoing link. So R2 will make one copy for this link and will generate one copy of the packet for this link, right? So by the way, this is called in-network duplication, and it's a sort of flooding approach. So there are two types of flooding approaches here that we like to discuss. So if we want to achieve broadcasting, then we have to use some sort of flooding, right? So we have to flood the network, right? So one type of approach for flooding is known as uncontrolled flooding. Uncontrolled flooding. And the second type is known as controlled flooding. Right. So so what happens in the uncontrolled flooding is that each source node sends a copy of the packet to all its neighbor, right? So in this case, R1 will send one copy to its neighbor R2, right? And if when a node receives a broadcast packet, it duplicates it, right? As I've discussed earlier, that R2 will generate one copy for each of its outgoing link. But clearly, if the graph is connected, this scheme will eventually deliver a copy of the broadcast packet to all the nodes in the graph, right? Although this scheme is simple and yes, elegant as well, but it has a fatal flaw. That is, if a graph has a cycle, right? So then one or more copies of each broadcast packet will cycle indefinitely, right? Creating broadcast strong. So this can create broadcast strong. What do you mean by broadcast strong? Broadcast strong results from the endless multiplication of broadcast packets, right? So this results because of the endless multiplication of broadcast packets. All right. So so this means that would eventually result in so many packets, broadcast packets being created that the network would be rendered useless. So so for example, in this case, obviously R3 will generate a copy for R4, and R4 will generate a copy for R3. But R4 and R3 have already received the copy of the same packet. So clearly, this is resulting into an endless multiplication of broadcast packets. This means broadcast strong. There are at the moment in order to achieve broadcast, either we can use source duplication, that is N-way Unicast to broadcast a packet, or we can use in-network duplication, which is basically representing this uncontrolled flooding approach that might result into a broadcast strong, means endless multiplications of broadcast packets. Right. So there is another type of flooding approach that is listed here, that is controlled flooding. So let's try to look at the example of controlled flooding. Right. So this reverse path forwarding is an example of controlled flooding. So this is in fact uh, a controlled flooding approach. Controlled flooding. So we will see how we can achieve this controlled flooding using reverse path forwarding. So the principle behind reverse path forwarding is that a node will only forward a packet to its outgoing link if it is receiving a packet from the shortest path back to source. Okay, let's try to understand this. So for example, this is our source node. Let me associate cost with each of these links. So the cost to reach from A to C is 2. The cost to reach from A to B is 3. And the cost to reach from C to B is 3. Okay, and the cost to reach from C to F is 1. The cost to reach from C to E is 2. The cost to reach from E to F is 3. And similarly, let's assume that the cost reached from B to D is say 2, and the cost reached from D to G is 2, and the cost reached from D to E is say 3. Right. So, what do you think? What's the least cost from router C to back to source A? Is it this cost? Is it this link having cost 2, or do you think it's this cost? Means from A to B and then B to C. Obviously, if I take this path here, the cost is 3 plus 3, 6, right? And if I take this path, which is the C being the direct neighbor of A, the cost is 2. So C will only forward a packet, only process a packet if it is coming from A through a shortest path to C, right? So this is called reverse path forwarding. If the reverse path back to source is the shortest path, then C will forward it to the outgoing link. Okay. So similarly, what do you think was the least cost from B to back to A? Is it this cost, which is 3, or is it through this path, means from A to C and from C to B? So this is 5. The total cost in this case back to source A is 5, but in this highlighted link or using this path, the cost is 3, right? So again, we will only forward a packet if it is coming from this path back to source A. Okay, so this means if B receives a packet from C, B will not process it, right? And similarly, if C receives a packet from B, this will not process it. Why? Because it is not coming from the shortest path back to source A. Similarly, now if F receives a packet, so what do you think, which path is the least cost to receive a packet? It is back to source A. Is it this path, which is what, 1 plus 2, 3, or is it this path, from A to C and then C to E and E to F? So 3 plus 2 plus 2. Obviously, this cost is more. So F will only forward a packet if it is coming from this path, which is the shortest path back to source A. Okay, and similarly, here E will process a packet if it is coming using this path, which is the shortest path back to source. And anything that is forwarded by E to F will not be processed, and anything that is being forwarded from F to E will not be processed or forwarded on the outgoing ports. So similarly, here we will D will process a packet if it is coming from this path, which is the shortest path back to source. Why? Because 2 plus 3 is 5. And if I take this path, or if I take this path, this is obviously not the shortest path, right? And anything that is forwarded to E by D will not be processed. Anything that is forwarded to D by E will not be processed. And similarly, this is the path that will be used by G, right? So this is called reverse path forwarding. So using any of the unicast routing algorithms, I can compute the shortest path from a node back to source machine, and I will only process a packet if it is coming from the shortest path back to the source machine. So using reverse path forwarding, I can definitely avoid broadcast wrong. So this means using controlled flooding or using reverse path forwarding, I can avoid broadcast strong. Right? So the problem here is that it does not avoid the transmission of redundant broadcast packets. Okay, see how. So, so that's okay that we will not process a packet that is coming from C, but B will still receive packets from C, right? So this is the redundant transmission of a broadcast packet. C will still receive, packets from B. Similarly, E will still receive, packets from F, and F will still receive packets from E. And similarly, D will still receive packets from E, though it will not process and forward it, but it will still receive the redundant broadcast packets. And similarly, E will still receive packets from the source D, right? So this means we need to come up with a solution. What if we only forward packets along this path, the highlighted path, right? So this means the packets will be only forwarded through this highlighted path, and a machine will not forward a packet other than the highlighted links, right? So I can think of it as tree of nodes, right? Where the different nodes are connected with this tree, right? And if I only forward packets along this tree, there won't be any redundant transmission, right? So by the way, this is if I only take this path, which is the highlighted path, this is an example of spanning tree. So this tree, the tree that is connecting these different links in this way, is called spanning tree, right? So basically, a spanning tree is a tree that contains each and every node in the graph, right? So I can say a spanning tree is a tree that contains each and every node in a graph. Okay, and if the total cost of the tree is minimum, so we call it a minimum spanning tree. So if each link has an associated cost, which is the case in our example, and the cost of the tree is the sum of the link costs, then a tree whose cost is minimum of all the graphs spanning tree is called minimum spanning tree. Okay, so next thing that you need to understand and note is minimum spanning tree. Right. So the case is that we can have many different trees here. So a tree which a tree with the minimum cost of all the graph spanning tree is called minimum spanning tree. Okay. Right. So this means to further avoid the problem of the transmission of redundant broadcast packets, we need to come up with, we need to establish a spanning tree, and there are two a minimum spanning tree wherever is possible. So the spanning tree can be of two types. Either we can have center-based. We can construct a tree using center-based approach, where there is only one tree for the whole graph, and this is also called the center node, or the core node is also called rendezvous point or core, right? So the node is for the center-based approach is also called rendezvous. Point or a core. Right. So the router that we are constructing tree keeping in point in consideration is called the rendezvous point or a core. The second way to construct a tree is source-based tree. Source-based, where depending upon a source, we will construct a spanning tree. So, for example, if I look at this figure, so this is a tree that is based on a source A. So, in this tree, the source is A, and this is the path that will be followed by all the broadcast packets, right? And now this is the tree that we have constructed considering machine D as source, right? So now this tree will be followed for sending all the packets, broadcast packets in this network, right? So you can clearly see that with the change in the source machine, because there was the source A, and here we have D as a source. So this means we'll have different tree for different sources. But in a center-based approach, we will have only one tree constructed based on a rendezvous point or a core router that will be used for sending the broadcast packets. So this is an example of center-based construction of a spanning tree, right? So clearly here, the center is E, the rendezvous point or the core router here is this node, right? E. Okay, so this is how different machines are joining this core or the center, the rendezvous point to make a tree. So in this case, no matter which node is the source node, the same tree will be followed. For example, if I want to send data, A is the source, this is the tree that will be followed. If we want to send data, G is the source, this is the tree that will be followed. So we won't be constructing a tree every time for a new source, right? So one tree is being used for all the sending machines or the source nodes, and obviously constructing a minimum spanning tree in this case is a very complex problem, is an NP-complete problem. So let's talk about the multicast routing now. So as we have discussed earlier, that multicasting is a subset of broadcasting. So we have understood the problem of sending n number of copies of a broadcast packet depending upon the number of nodes in the network and the possible techniques to achieve it. We have controlled flooding, we have uncontrolled flooding, and the more appropriate approach to achieve broadcasting was reverse path forwarding. Multicasting means that we have to send a copy of your packet to some selected nodes, but not all the nodes in the network. So that's why multicast routing is, or multicast routing problem is a subset of broadcasting, right? So there can be many different examples where we would like to send a copy to n number of machines rather than to all the machines in the network. For example, we want to make a bulk data transfer where we want to transfer a software upgrade from the software developer to the users who are needing the upgrade. Or for example, we are using a streaming continuous media where we want to send audio or video or a text of a live lecture to a set of distributed lecture participants, or there can be a shared data application. For example, we can share a whiteboard or teleconferencing application that is being shared among many distributed applicants. Or in other examples, we can have a data feed, for example, the stock exchange, or we can have web cache updating or interactive gaming. Before discussing multicast routing problem, let me talk about the important concepts related to multicast routing. So in multicast communication, there are two problems that we immediately need to find a solution of. So I want to talk about the problems that we immediately faced in multicast communication. Number one problem, there are two basically that we want to discuss. Number one is how to identify the receivers of a multicast packet. How to identify the receivers of a multicast packet. Number two, how to address a packet sent to these receiver. So how to address a packet sent to these receivers. Because in the case of unicast communication, the IP address of the receiver or the destination is obviously carried in each IP unicast datagram, and it identifies the single recipient. And also in the case of broadcast, all nodes need to receive the broadcast packet. So node specific destination addresses are needed. But in the case of multicast, we now have multiple receivers. So it does not make sense for each multi-packet to carry the IP addresses of all the multiple recipients. So there needs to be, maybe this is workable for a small network, but it's not suitable for a network having thousands of receivers, right? So that's why we need to come up with some sort of solution to address these problems. For these reasons, in the internet architecture, a multicast packet is addressed using address indirection. So the concept that we want to understand is address indirection. So address indirection means that a packet is multicast packet is addressed using address indirection. So a multicast packet is addressed using address indirection. Right. So this means that there is a single identifier that is used for the group of receivers, and a copy of the packet is addressed to group using this single identifier. Will be effectively delivered to all the multicast receivers associated with that group. Right. So in the internet, by the way, the single identifier that represents a group of receivers is a class D multicast address. As we have covered this earlier as well, that class D is used for multicasting. We use an address of class D to refer to a multicast group. Right? So this means a class D address is referred to as a multicast group. Right. While the multicast group abstraction looks simple, but there are obvious questions that we need to find answers of. For example, how does a multicast group get started, and how we can terminate a group? And for example, how is the group address chosen? Where are the new hosts added to the group? Can anyone join a group, or is there any group membership restricted? And if so, by whom? And similarly, do group members know the identity of the other group members as a part of the network layer protocol? How do the network nodes interoperate with each other to deliver a multicast datagram to all the group members? So there are many questions to answer to, right? And the answers to all of these questions involve and requires, in fact, a protocol that is known as Internet Group Management Protocol. So if I want to achieve multicasting, I need to make use of, you need to understand Internet Group Management Protocol. IGMP. Okay, so this details are obviously given in RFC request for comments 3376. So at the moment we have Internet Group Protocol version 3 that operates between a host and its directly attached routers. IGMP has only 3 message types for its operations. And by the way, like ICMP, IGMP messages are carried within an IP datagram. So like Internet Control Message Protocol, IGMP Internet Group Management Protocol, messages, a caret, within or encapsulated within an IP datagram. IGMP has three types of messages. Number one, we have membership query message. Membership query message. So the membership query message is sent by a router to all the hosts on an attached interface to determine the set of multicast groups that have been joined by the host on that interface. This message is sent by a router to all hosts on an attached interface. And purpose is simple. The router is interested to know that a host has associated with how many number of multicast groups. Okay. The second message is membership report. Membership report. So the hosts respond to a membership query message with an IGMP membership report message. So membership report message, by the way, can also be generated by a host when an application first joins a multicast group without waiting for a membership query message from the router. This membership report is either generated in response to the membership query from a router, or it can be generated without waiting for a membership query from the router in case where the application first joins a multicast group. And the number 3 message is called leave group. Leave group. So final type of IGMP message is the leave group message. So by the way, this message is optional. But if it is optional, then there is an obvious question that how does a router detect when a host leaves the multicast group? Okay, and the answer to this question is that the router infers that a host is no longer in the multicast group if it no longer responds to this membership query message within the given group address. For example, this is an example of what is sometimes called soft state in an internet protocol. So these are the three types of messages that are used by IGMP Internet Group Management Protocol to implement multicasting. Let's try to understand the goal of multicast routing. So what is the problem statement of multicast routing? It's very simple. The goal of a multicast routing is to find a tree, or maybe trees, that is obviously connecting routers having local multicast group members. So this means the goal is to find a spanning tree in the case of a source-based tree, or to find a tree in the case of a shared tree, right? So tree means not all the paths between the router used, that we have already covered. So we have already discussed this, that we can have two types of, we can tree either based on the source, or there can be a shared tree. So look at this example. Here we have source-based tree, and now we are assuming, by the way, these routers represented with red colors are representing that these are having attached with them some multicast group members that are being also highlighted with the red color. So here is a group member, say this is the source now, right? And now we have created this tree for this spanning tree for this source under consideration. So I will follow this path for sending data to all the different nodes if I'm using source-based tree. But if I change the source, and let's assume that this is the source now, this machine. So this means I have to reconstruct the tree now. And now this is the tree that is being represented with this blue color here in the diagram, right? Now I will use this tree to send a multicast packet to all the multicast group members here. But in the case of shared tree, we have one tree that will be followed regardless of the source machine. So if this is the source, we have the same tree to be followed. And if now the source has been changed and this machine is sending data, still the tree is the same. We will not be constructing the tree for keeping the source in consideration. So here we have the shared tree that will be used, and here we are talking about the source-based tree, which obviously here I would like to have a spanning tree, a minimum spanning tree, right? Where the link cost is minimum, right? So there are two approaches, as we have just discussed, to construct our tree, to build a tree. Either we have the source-based tree, one tree per source, right? And obviously here we talk about the shortest path trees, and these trees are constructed using reverse path forwarding, right? So using any of the Unicast routing algorithm, what we'll do, we'll try to find the shortest path back to source using reverse path forwarding, right? And we'll try to come up with a tree which is minimum spanning tree, having the least cost to reach all the multicast group members, right? But if we talk about the shared tree or group shared tree, where a group of multicast nodes are sharing a tree, so this tree is basically now based on a center-based tree or a rendezvous point-based tree, and constructing a minimal spanning tree is a standard tree problem. It's a difficult job to find a tree which is the shortest tree for each and every source machine in the network. It's a difficult job, right? So first let us look at these basic approaches, and then we'll look at the protocols that are basically implementing these basic approaches. So let's talk about the shortest path tree, the spanning tree, right? So here, for example, this is the source, and now this tree is based on source-based. I have to find the shortest path back to source. Say to identify the shortest path, I'm making use of Dijkstra's algorithm. I can also make use of Bellman-Ford, by the way, right? So again, this way I will construct a tree that will be followed to send multicast packet to all the group members attached with this tree. And similarly, you can clearly see that there are no group members attached with router R5 and router R7. So these routers can send prune messages to R4, so that they are not willing to receive any multicast packets anymore, since there are no group members attached with these routers. So the reverse path forwarding is very simple. That is based on the router's knowledge of the unicast shortest path from it to sender. And for the unicast shortest path, we can either make use of Dijkstra's algorithm, or we can make use of Bellman-Ford. So each router has a very simple forwarding behavior. That is, if a multicast datagram received on an incoming link on the shortest path back to center, then it will flood onto all the outgoing links. Else, it will ignore the datagram. It will not forward it to the outgoing interfaces. So this is an example of reverse path forwarding. So similarly, if R1 has to forward data to R2, so R1 will forward it to R2, and R1 will also forward to R4. Now R2 has its shortest path back to R1 using this path, so it will follow this path. Anything that is coming from this path will not be forwarded. Anything coming from this path will not be processed by the R4, right? And similarly, we'll select this path and this path, and anything coming from router R3 to R6 will not be processed and forwarded, and anything coming from router R6 to R3 will not be processed and forwarded. And same is the case over here as well, right? So so in this way, we will, using reverse path forwarding, we will end up establishing a tree that is highlighted here, and we'll call it what? A tree which is source specific. Why? Because this tree is constructed considering the source into concentration. So this might be a bad choice, especially when we have asymmetric links. So similarly, as we discussed earlier, if since R5 and R3 has no multicast group members, so there are no multicast group members here. So they can send what? They can send the prune messages to the upstream router, so that they are no more part of this spanning tree, means they will not be receiving any multicast group members in future. So let's talk about the shared tree, and it's also called Steiner tree. Steiner tree means minimum cost tree connecting all the routers with attached group members. So finding a tree which is minimum for every host is, as I discussed earlier, is NP complete problem, right? And that's why it's not used in practice. Why? Because it has high computational complexity, and for that I need to have the information of entire network, and it's obviously monolithic. I mean, I have to rerun whenever a router needs to leave or join. I again need to rerun it, having the information about all about the entire network, and obviously it involves complexities. It has high complexity as it's NP complete problem, right? So center-based tree means that we have a single delivery shared tree that is being shared by all the sending nodes. An edge router sends unicast join message addressed to the sender router, right? And then this join message is processed by the intermediate routers towards the rendezvous point or the center router. So it's possible that the join message hits an existing branch of the tree, or maybe it reaches to the or it arrives at the center, right? The path taken by the join message becomes the new branch of the tree for this router. Similarly, the other routers can join the rendezvous point or the center router to make a center-based tree. So in center-based tree, let's look at this example. Let's assume that this is the core router here, R6, and the other multicast, other routers having multicast group members attached with it will send path messages in order to join the core router, and these path, the paths that are taken by the join messages will make the center-based tree in this case. Let's talk about the multicast routing protocol. So first we'll discuss distance vector multicast routing protocol. As you can see, that is based on the distance vector. and these details are given in RFC 1075. It uses prune and flood messages to make a source-based tree. So, the important point here to understand is that DVMRP is based on source-based tree, right? And obviously, it makes the use of reverse path forwarding to construct a tree for every source. So every time we have a new source, we'll come up with a tree for that specific source. So reverse path forwarding based on distance vector's own routing tables constructed by communicating distance vector multicast routing protocol. So there are no assumptions about the underlying unicast routing algorithms. Why? Because it makes use of, yes, you're right, distance vector routing algorithms, right? So routers that are not willing to, be part of the group because there are no multicast group members are attached. They can all always send this prune message to get. Then obvious question about the internet multicasting is that how to connect island of multicast routers in a sea of unicast routers. So all these routers, represented with these gray colors are unicast router, and the routers represented with these red colors are multicast routers. So how to route data from this multicast router to this multicast router, where there are many different unicast routers. So the problem is very simple. So what we can do is that we can set normal IP datagram through a tunnel. That is, the multicast group members will be multicast datagram will be encapsulated inside the normal datagram, right? And when it is received by the multicast routers, it decapsulates it and process it accordingly. So let's talk about the second type of multicast routing protocol. It's called protocol independent multicasting, because here we are not dependent upon any specific underlying unicast routing algorithm, which was the case with distance vector multicast routing protocol. So in distance vector multicast routing protocol, we were supposed to use distance vector to calculate the shortest path back to source, but in protocol independent multicast protocol, I can either make use of distance vector routing algorithm, or I can make use of Bellman-Ford algorithm. So it has two it has two different scenarios. It has a dense mode, or it has a sparse mode. Dense means that the group members are closely parked and they're in closer proximity, whereas in sparse mode we have small group members. Then here the bandwidth is plentiful and dense, whereas the bandwidth is not plentiful in the sparse mode. In the sparse mode, group members are widely dispersed. There are few in numbers, but the basic difference between the PAM dense and the sparse mode, if we talk about its dichotomy. So here the multicast trees are based on reverse path forwarding, right? This means what? This means here we will be constructing tree for each source, right? So this is source-based tree in PAM's dense mode. And if I talk about the protocol independent multicasting sparse mode, it's basically receiver-driven construction. Means it depends upon so this means it's based on a center or a rendezvous point. So here we construct a multicast tree by using center-based approach. So this concludes our today's lecture. In this lecture, we discuss the problem of broadcasting and multicasting. See, the problem of multicasting is to send a packet to all the nodes in the network. So one simple way to do is to say that a source will send n number of copies depending upon the number of nodes in the network. This is called n-wave forwarding. But the problem with this approach is that this is an inefficient way of sending the packets, as it will traverse a single link. A packet will traverse a single link many times, and this is called, by the way, source duplication. And the other approach is to do in-network duplication, whereas source sends one copy of the packet to its neighbors, and the neighbors generate multiple copies of the packets depending upon their number of their outgoing links. This is, by the way, known as uncontrolled flooding approach, and this might result in broadcast storm. And if we want to avoid the broadcast storm, then we discussed that we have to construct a tree based on reverse path forwarding, which is called controlled flooding, and the tree that we'll construct is called a spanning tree. And the goal is to develop a minimum spanning tree depending upon specific source. So we can either construct a tree based on a source, or we can have a single tree for all the multicast group members. And then we talk about the problem of multicasting, which is the subset of broadcasting. That the problem of multicasting is to find a minimum spanning tree for each of the source, and to construct a group-based tree. Obviously, if we want to construct a group-based tree, minimum spanning tree, it's a difficult job because it has a lot of complexity. It's a complete problem, and then we need to have the information of all the nodes in the network, and this is also monolithic in terms that we have to redo it every time a node joins or leave the network. Then we discuss the routing multicast routing protocols such as DVMRP. So distance vector routing, distance vector multicast routing protocol. In fact, builds the source space tree, and for the sake of identifying the shortest path back to source, it uses this distance vector unicast algorithm. Right, and the second protocol that we discuss, protocol independent multicasting. It is basically independent of any specific unicast algorithm to calculate the shortest path back to source. It has two modes, either the dense or the sparse mode. The dense mode is basically is based on the source space tree, where we construct a tree based on reverse path forwarding. So for every source, we'll have a different tree. Whereas the sparse mode is based on the center-based tree, where we construct one tree that is used by all the nodes to forward multicast packets. Dear students, thank you very much. Allah Hafiz.